what kind of cell could that be? That could be another neuron, that could be a glial cell, that could be an epithelial cell, that could be whatever, it doesn't matter. It's some other cell that this neuron wants to communicate with. And the information is flowing from left to right. This neuron is communicating with that cell. How is it communicating? Action potentials. That's how it's going to communicate. So what I'm going to do is, and this is going to be an electrical synapse, is what we're showing. Actually, you know what? Let's just label it specifically. There is our electrical synapse. Put it on the top because we're going to draw something underneath. That is the electrical synapse. And we're going to magnify it. So the electrical synapse is right there. All right? So let's magnify this area right here. So we're going to box that in, and now we're going to magnify it. All right? So I'm going to draw the very end of that presynaptic term. So that's what that is. So that's part of the axon, obviously. Actually, we're going to put a little hole in there. You'll see why. Same thing with that other cell, the membrane of some cell. This is the membrane of that cell. Put a little hole in it as well. All right? So that's some cell. Again, doesn't matter what kind of cell it is. It's just a cell that's being communicated with. It's a cell that's being told something. The reason we have that space in between both of those membranes is because we're going to draw a channel in between those two membranes, in between those two cells. And that channel has a special name that you're well aware of. That's a gap junction. This has got to be at least the third time you've heard the word gap junction. A gap junction is really just a channel in between two cells that allows electrical communication. So we can plainly see that the cytoplasm of that axon is open to the cytoplasm of that cell. And that allows communication between those cells, and it is very fast. If we had to compare the speed at which information is transferred from this cell to that cell electrically, and we compared it to a chemical synapse, it's not even close. It's pretty much just one step, or at least that's all we need to know. So we have flow of information through that gap junction. And by the way, the gap junctions can open and close just like other channels can. Okay? So those can open and they can close. And when they're closed, you won't have any communication. And when they're open, you will. Why do they open and close? Because that's what's supposed to happen. Obviously then, sometimes things can go wrong, and they close when they're not supposed to, they're open when they're not supposed to, and then bad stuff happens. But for right now, let's just keep with the good stuff, and we assume everything's working, and they're opening and closing the way they're supposed to. That is an electrical synapse. Now, there's some anatomy behind this that we don't have to worry about. Okay, I used to talk about it, and I just don't see, you know, if Steve wants to talk about the anatomy of these things, it's fine. I'm just going to stick with FIS. So what don't you have to know? What can you cross out? All that. Connect sons with an O, connect sins with the I. Those are the proteins that make up, or the structures that make up the gap junction. All I'm worried about is gap junction. Gap junction, electrical synapse. That's what you should equate with each other. All right, and the information that's being passed from one to the other is very fast. It allows for coordination, it allows for speed, and we'll see that later on in the semester when I talk about cardiac muscle and smooth muscle, for example. Because again, electrical synapses are found in other places other than neurons, as we'll see. That's all you have to know. All right, again, very, very fast. We can just say it's one step. Boom, one step. Is it more than that? Yeah, but we're going to keep it simple, one step. Because I want to make a direct correlation, or a comparison, I should say, between an electrical synapse and a chemical synapse, which is what we're going to talk about next. So now let's talk about a chemical synapse. We're going to spend a lot more time on this because it's a lot more complicated. So the chemical synapse involves other anatomical structures that you're very well aware of. You have the presynaptic membrane, the postsynaptic membrane, the synaptic cleft, you have neurotransmitters, you got receptors, you got all kinds of stuff going on here. And these are all terms that you should be very well familiar with. Do you have a quiz on this today too? Is this stuff on the quiz? If it is, we're gonna get a little bit of review with a bunch of fizz. If not, well, we're just gonna review, okay, in detail though. So what are we gonna do now? We're gonna draw a chemical synapse, and after we're done doing that, we're gonna go through a list of events that occur that allow it to work. So we're gonna draw the neuron again, although we didn't have to draw a neuron, but we're going to, because again, that's what you're familiar with right now. So we have our neuron again, and we have our presynaptic terminals again. We'll draw one a little bit longer than the others. And now we're gonna have some cell again, but now we're not going to have it touch that membrane so that we can see there's a distinguished anatomical feature about the chemical synapse. Again, information is going from left to right. This is some cell. Again, it doesn't matter. It doesn't matter what's it could be a muscle cell, it could be a glial cell, a neuronal cell, an epithelial cell, it doesn't matter. And so what we have here is this area right here. That's our chemical synapse. Now I put a space in between those two because there is a space in between those two called the synaptic cleft. So let's magnify that and see what it looks like. So we have many more anatomical structures that we need to put in this picture. So there's our presynaptic terminal. Again, that's where the information is being generated from. All right, so this membrane right there would be the presynaptic membrane. Again, this is all review to you guys. I know that Siebert went over it, but I'll refresh your memory because it's important to know these anatomical structures to understand the fizz. This is the membrane of that, whatever the hell cell it is. So again, that's some cell. That is the postsynaptic membrane. And there's a few other structures that we must draw in this picture. I'm going to draw these little circles with dots in them. You can tell me what those circles are, can you not? They're synaptic vesicles. What are the dots called? So neurotransmitters. Although not all neurotransmitters are inside of vesicles, as you will learn shortly, actually in this lecture, because we still have 25 minutes. What else do we need to draw in this picture? That's important for us to know. These things right here. What those are receptors. We're very familiar with what receptors are. These are the receptors that we talked about in that second chapter at the beginning of the semester. Those receptors have a job, that is to grab some specific, right, specificity, some specific molecule. In this particular case, the job of these receptors is to grab the neurotransmitter, and it's going to be a specific neurotransmitter. We'll talk about specific neurotransmitters on Wednesday. We're going to get through about a dozen of them. Although there's about 60 to 70 different kinds in your body, we're going to talk about a fifth of them. All right? So, those are the anatomical structures that are important for you guys to know. You already did know them. In order to understand chemical synaptic transmission, communication between this and that. All right? So, we're going to draw the picture again on the next page, and we're going to number it just the way we did with the action potential. So there are a number of events that are going to occur that allow communication. Again, when it comes to an electrical synapse, one step. This is going to be about 7. All right? And that's very simplified. There's really probably about 100 steps, many of which I don't even know. That's all biochemistry. The black hole of information, as I like to call it. So, there's the presynaptic terminal. All right? Again, we're drawing the same picture we did on the other page. That's some other cell. Here are our receptors. Oh, one other thing. What's this space called? You might as well be thorough here. What's that called? Synaptic cleft. All right. We're going to draw our vesicles in here. Let's draw, I don't know, 4 of them. Although there's a hell of a lot more than that. Well, actually, there was another structure that we need to draw in the picture that we didn't on that other page. Wait, we're going to do it here. Right here, that right there is a voltage-gated channel. But it's not a voltage-gated sodium channel. It is not a voltage-gated potassium channel. It's not the 2 channels that are responsible for action potentials. That voltage-gated channel is a voltage-gated calcium channel. There are all kinds of different voltage-gated channels in your body, guys. All right, here's a third one. And it's a very important channel because if it's not present and if it's not working, none of this works. All right? So, how are we going to get this to communicate one cell to the next? Step number one, we need, and let's put our voltage gated calcium channel up here. Step number one, we need our action potential to get to the very end of that presynaptic terminal. How did it get there? How did that action potential get there? Through what? Start with a C. Conduction. How did that last action potential get there? That's how it got there. Either continuous conduction or saltatory conduction. The very last action potential ends up at the very end of the terminal. Again, it's about communication. Why do action potentials happen? For many different reasons. One of them is communication. Getting the action potential to conduct along the membrane of this particular neuron will allow for communication, electrical and chemical. Without this action potential at the very end of that terminal, none of this is going to happen. That has to happen. So step number one is an action potential at the very end of the presynaptic terminal. What's step number two? That's going to open those voltage gated channels. That will depolarize the membrane right here to a point to where we reach threshold and it pops those calcium channels open. And so step number two is the opening of those channels and calcium concentration going up. By the way, what words are we talking about in your notes? These. We're about to draw this. That's what we're going to draw. And so what have we drawn so far? Well, look at the first line. Action potential travels to synaptic terminal of the presynaptic membrane. That's number one. Causes voltage-gated calcium channels to open, which increases intracellular calcium concentration. That's number two. Number three. When that calcium concentration goes up, which again is step number two, what that's going to do is it's going to cause the synaptic vesicles to literally move. They are going to move in this direction. Not all of them, okay, but a certain percentage of them. So we're going to depict that by drawing them dotted, or at least that's how I'll do it. Do it any way you want. We have to put our neurotransmitters in there. What that's showing is that they were once at point A, now they're at point B. That's step number three. So, the vesicles membrane is going to fuse with the membrane of that presynaptic terminal. You tell me what happens next because we already learned it, and you can go ahead and tell me what the name of it is. What process is going to happen next as a result of those two membranes fusing with each other? It starts with an E. Exocytosis. I even showed you a picture of it back when we talked about transport. What do we need for that to happen, by the way? Just to make sure I know you guys remember stuff. Is it an active thing? Do we need ATP? Is exocytosis an active transport process? All right, we weren't going to put it in the picture. I just wanted to just make sure that you guys remember. So, number four, we're going to get exocytosis of the neurotransmitter. And so now it's in the synaptic cleft. So number four, release of neurotransmitter. We have exocytosis. Again, it's in your notes. We're just following what's in your notes. And now that that neurotransmitter is in the synaptic cleft, it's going to diffuse across the synaptic cleft until it reaches its destination, until the receptors that are sitting there grab it, because they're specific for it. So, go ahead and draw little dots on the receptors. And it's not going to hit every receptor, by the way. So, number five. And write it in your notes. So, binds, what binds? Neurotransmitter binds to specific rep. That's number five right there. Number four, neurotransmitter is released into synaptic cleft via exocytosis. That's number four. Number three, synaptic vesicles fuse with the membrane, blah, 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 blah. Okay, so just again, in the margins, put the numbers down so you know exactly what all these numbers mean. All right? So, number five, we bind to these particular receptors. Number six, a word that we've used and I've used in the past. Stuff happens. What kind of stuff? Stuff that we really didn't learn. A lot of biochemical stuff. The receptors binding that neurotransmitter causes stuff to happen inside the cell. What kind of stuff? Again, we don't need to worry about. But what does